All right, let's talk about the rules. The rules meaning like the product rule and the quotient rule and the chain rule and all that good stuff. So we want to find the derivative of something like x cubed times sine of x. And for something like this, you really are forced to use the product rule, which I know we haven't explicitly said in this class, but we're about to. So when I'm thinking about the product rule, I'm just thinking about two things being multiplied together. And when we take the derivative, it's the derivative of each part multiplied by the not derivative of each other part. So it's the derivative of x cubed. And some people like to take this extra step here. I don't personally, because it's more writing than I want to do. But we could say it's the derivative of x cubed times sine of x left alone plus x cubed times the derivative of sine of x. And then we actually go find the derivative. So the derivative of x cubed is 3x squared. Sine of x is just sine of x. X cubed is x cubed. And the derivative of sine of x is cosine of x. Which I know we briefly talked about a couple classes ago, how the derivative of sine was cosine and the derivative of cosine was negative sine. We're definitely going to be using those facts a lot. So it's good to kind of get them down. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. I definitely saw that Dr. Tab did talk about he did the limit definition of the derivative of sine. We could certainly address that if we feel like we need to, or we could just kind of go with it. We'll circle back around then when we talk more about the derivatives of the trig functions today. So the product rule is great. It just says if you're trying to take the derivative of two functions multiplied together, actually, let's say what it's not first. I'm not going to write it down, but I just want to point out the product rule is not that you just multiply the derivatives together. The derivative of f times g is not f prime times g prime. It is equal to f prime times g plus f times g prime. Come on in. We're just talking about the product rule. It is a rule. In fact, we might as well, because we're not going to do it for the quotient rule. So let's go ahead and actually see how you would show the product rule is true. I don't think you need to write this next part down if you don't want to. I just want you all to really, really believe the product rule in your heart. So the way you would show this, or the way you would show anything is true, really is you'd go back to the limit definition. So if I actually wanted to find, let's get myself some room here. If we actually wanted to find the derivative of f of x times g of x, well, limit definition, it'd be the limit as h goes to 0 of, you take that function and you plug in x plus h. So f of x plus h times g of x plus h minus f of x times g of x, all divided by h. Limit definition, right? The usual kind of thing. You just say the thing you have with x plus h in it minus the thing you have with just x in it, all divided by h. And if you plugged in h going to 0 right now, you get 0 over 0, undefined. We have to do more work. And this is where you kind of have to. So a lot of math sometimes is someone has shown you how to do it once, right? Like I would never know how to do this next part unless someone had shown it to me before. The next part's kind of a trick. We're going to add and subtract something convenient. So I'm going to leave myself some space. I have f of x plus h times g of x plus h. Bunch of space here. And then over here at the end, minus f of x times g of x. What I'm going to add and subtract is, actually I have to remember myself with this. I'm going to subtract off an f of x plus h times a g of x. And I'm going to add on an f of x plus h times g of x. That'll work, yeah. Why did I do that? Well, here's why. And I'm going to break this up into two fractions with the limit as h goes to 0 of the first fraction being these two pieces. So f of x plus h times g of x plus h minus f of x plus h times g of x all over h plus this other fraction, f of x plus h times g of x minus f of x times g of x. Now let me ask all of you, from the numerator of this first fraction, what can I factor out from each of these two terms? The f thing or the g thing? The f thing, right? The f of x plus h, because I have an f of x plus h in each of these two terms. So I can rewrite this part as the limit as h goes to 0 of f of x plus h factored out times g of x plus h minus g of x all over h. That should look familiar. Over here, same deal. What can I factor out from all of these things? Or each of these things? So I'm going to write it like this, f of x plus h minus f of x all over h times g of x. Okay, now here's where we have to actually see a thing. Ignoring this for a second, if I took the limit as h goes to 0 of g of x plus h minus g of x all divided by h, that looks like the limit definition of the derivative of g. So I can say that the limit of this is really g prime of x. It is actually the definition of the derivative. So if I let all the h's go to 0, I get f of x, because h is 0. Here is the derivative of g, plus same deal here. The limit as h goes to 0 of this is also the derivative. That's the limit definition of the derivative. So that's going to be f prime of x times g of x. And I got this out of order because I made not the wrong choice, but a different choice than is typical. But it doesn't matter what order you multiply things in or add things in. So we could totally rewrite this in the more standard order of f prime of x times g of x plus f of x times g prime of x. And we just proved the product rule. Do you have to be able to prove the product rule? Not at all. Is it nice to have seen it? Yeah, it's nice to see it to kind of make it a little bit more believable. So, product rule is great whenever you have two things multiplied together. Let's look at some examples. Let's look at some examples. So let's say we have something like f of x equal to, I'm a real big fan of ones with trig functions, so otherwise you kind of just multiply it out. Here's what I mean. Let's say we had f of x equal to, sure, x to the 7th times, oh, that's a good one too, cosine of x. I'm just going to throw the product one. I'm seeing the product one here because I have things multiplied together. So my derivative here, if you like, you can kind of think of like this is, I wouldn't use f again because I already used f. Like this is a g and this is an h, and then I write g prime h plus g h prime. I don't think you really need to write any of that out. I'm thinking here, derivative of x to the 7th is, all right, here's the important part. What do I multiply that by? Just cosine of x. We leave the other thing alone. It's always the derivative of one piece and leave the other piece alone and then switch it up. So then I'm going to have x to the 7th times negative sine of x. If it were me and I was cared, I would rewrite this as 7x to the 6th times cosine minus x to the 7th times sine, but I don't care that much right now. What if I had something like, I don't love that. Fine, sure. Let's say we have g of x equal to x cubed plus x minus 3 divided by, that's the backwards way I was going to go. Sorry, that's not what I meant to do. Terrible. My brain got caught up. Sorry. Let's say we had sine of x divided by x to the 5th. And even if we have the quotient rule, I still wouldn't use it here. I would much rather first rewrite this as x to the negative 5th times sine of x. I suppose I should still say that's g of x equal to x to the negative 5th times sine of x. And then again, I can use the product rule here. When you are rewriting something, you should be writing that it's g of x or f of x, or whatever your function is called. Right? I shouldn't write g prime yet because I haven't started finding the derivative yet. So g of x is still x to the negative fifth times sine of x. And then g prime of x is going to be derivative of x to the negative fifth, which is negative 5 x to the negative sixth times sine of x plus x to the negative fifth times the derivative of sine of x, which is cosine of x. It is almost always a good idea to simplify something before differentiating it if you can, to make it easier to not have to use the quotient rule. You could rather use the product rule or. Yeah.
How come the example at the top with the cosine of x has negatives for x and is just positive?
Right. So sure. Let's talk about that. That's a good question. So the derivative of sine is equal to cosine. And there's a couple ways you can see that. One way, the way I kind of like to keep in mind, actually, so there is a limit definition thing, and we can actually talk about that, but I would rather you all know this. Sine looks like this. We spent a fair amount of time last class graphing it and other things. And if I was going to try and graph the derivative, so I know there's a couple homework problems where you're asked to like, here's some graphs and then max them up with the graph of the derivative, right? There's a few of those in one of the assignments. That's actually a really useful skill. When I'm trying to match up a graph with its graph of its derivative, I'm thinking, okay, I'm looking at the graph, that's the original function, and I'm trying to look at the slopes of the tangent lines because those values of the slopes are my derivative values. So just actually off to the side here, if my graph looked like this, and I was trying to graph the derivative. So here's my function. And I want to graph the derivative. So let me ask you, gosh, always with this, way over here to the left, is my derivative really positive or really negative? If I think about the slope of the tangent line, that slope is very positive or very negative? Very negative. So down here, my function, my derivative values should be very negative, meaning I'm down here somewhere because the value is negative, not the slope, but the actual numerical y value of my derivative. And then as I move further to the right, my slope is still negative, but less negative. So maybe I'm more like up here now. And then when I get to, I'm always looking at the places where I have maxes or mins, because right there, the slope of the tangent line is 0. And so the graph crosses from being negative, and I haven't drawn this very well, to being positive. Over here, slope of the tangent line is slightly positive. Over here, slope of the tangent line is more positive. So slightly positive, more positive. The derivative here is pretty much a straight line because the derivative of a parabola is like 2x. Oh, wow, that's really good. Anyway, the point is we can look at the original function and think about the value of the slope of the tangent line to kind of guess what the graph of the derivative would look like. And we can do the same thing for sine and cosine. If I think about this being sine, the derivative, well, the slope of the tangent line right there is actually 1. The slope of the tangent line here is 0. The slope of the tangent line there is -1. The slope of the tangent line there is 0. So the tangent line there is back to +1. And look, you've exactly got the look of your cosine graph. So the derivative of sine is cosine. And that's a nice way of seeing it. Now, let's do the same thing for cosine, which I should have left myself more room, but you know, I'm not great at planning ahead here. Let's say our function was now cosine x, which I know is graphed up there, but I'm going to graph it again anyway. So there's good old cosine. It really is, I think, important of all the trig functions to at least have a good idea of what sine and cosine look like in your brain. You should just know that sine looks like that. Sorry, you can't see it. Sine looks like that, right? It starts at the origin and then does this deal. Cosine starts at the 0.01 and then does this deal. If I try to graph the derivative of cosine, well, oof, okay. Right there, the slope of the tangent line is what? What's the slope of that line? Okay, thank you, 0. How about right here? Positive or negative? Negative. -1. I know it's not hard. It's not like an exact science to look at the graph and know what the actual value is. But you can see, especially for the sine graph here, that if you actually draw the sine graph correctly, the slope of that line, the tangent line really is the line y equals x, which we know has a slope of 1. And then over here, 0 again. Over here, 1 again. And at the end, 0 again. Ooh, did it? Yeah, sure. Okay. Got kind of stretched out there. So here's the graph of the derivative of cosine, which looks a lot like the sine graph flipped over, which is the negative sine graph. So the derivative of cosine is negative sine of x. So that is one way to know that when you differentiate sine, you get a positive cosine. When you differentiate cosine, you get a negative sine. And I will say broadly, whenever we differentiate a co-function, cosine, cosecant, or cotangent, you do get a negative derivative. And we will do those today. Whereas when you differentiate sine or tangent or secant, you get a positive derivative. And we'll see why. The other way of showing this is the longer way, like the limit definition. So in class, I know I saw he did the limit definition of the derivative of sine. He used some trig identities, and it looked kind of gross. Do we want to look at that? We don't have to. You guys are like, no, let's please not. All right. Questions about this before we move forward? That seem good, Is it Kelsey? No. No, it's oh, God, it's on the tip of my tongue. Nikki. No, is it Nikki?
Yes.
Okay, cool. Does that seem good? Okay. Yeah, so yeah, let's talk about the quotient rule so then we can talk about more interesting examples. Quotient rule. I think of the product rule and the quotient rule together. So I remind myself that, first of all, the product rule, the derivative of f times g, which sometimes we write just f times g instead of f of x times g of x, just because we're lazy, is f prime times g plus f times g prime. Here's the quotient. I know that's not the quotient rule. This is the product rule. But we're using this to help us see what the quotient rule is. So the quotient rule, the derivative of f divided by g, the numerator looks almost exactly the same as the product rule, which is why I think of it. Except instead of f prime g plus f g prime, it is f prime g minus f g prime. And so whereas the order in the product rule doesn't matter, right? It doesn't matter if you do 2 plus 5 or 5 plus 2, you get the same result. The order in the quotient rule definitely matters. 5 minus 2 is different than 2 minus 5. So you have to make sure you get the things right here. And then we divide by denominator squared. When I say the product rule in my head, the words I'm saying are actually slightly out of order. If I'm thinking of f over g, or the top thing and the bottom thing, the way I say the product rule is the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. That's how I think of the product rule when I'm saying the words in my head. Actually, I just learned not too long ago that not everybody has an internal monologue. So maybe you aren't saying the words in your head, but I'm definitely saying all the words in my head all the time. So if you're the kind of person that has an internal monologue and you're saying things to yourself in your head, like some of us do, apparently not all of us do, it seems weird to me, then that's what I would say. Bottom derivative of the top minus top to the bottom, all over the bottom squared. So for example, if I want to find the derivative of, say, I don't know, x squared plus 1 divided by x cubed minus 7, I'm just going to start off without really doing any work. I might do a little work. but I might not. I might just say, okay, it's going to be, now I'm going to write this slightly out of order. I'm not going to write f prime times g because it's just not the way I say it. I'm going to write g times f prime, the bottom times the derivative of the top, minus the top times the derivative of the bottom, all divided by the bottom squared. That does say x cubed minus 7. I know the minus sign looks like it's kind of stuck on the 3 there. I would not choose to simplify this unless someone asked me to, or unless someone said, find where this derivative is equal to 0. We could simplify it. It's not that terrible. If we distribute the 2x, we get 2x to the 4th minus 2x times 7 is 14x. Minus 3x squared times x squared is minus 3x to the 4th. Minus 3x squared times 1 is minus 3x squared. All over. I wouldn't multiply at the bottom. And then you could probably simplify the top a little bit more. But that is what we do if we're simplifying. Usually when someone is asking us to find derivatives of things, we are not going to simplify them unless there's a good reason to. So both, oh yeah, question.
As a second.
I would leave, personally, unless there was a reason to, I would leave it like this. One sec. I will point out that often we are going to be asked to find where a derivative is equal to 0. And so then it is worth simplifying because that makes it easier to solve that.
Well, I was just gonna ask if you know whether Mr. Tabernetti.
I would say so typically, again, I don't know for sure, and you should ask him really. Typically, when people ask like derivative questions on exams, there's usually a section where it's like, find the derivative and do not simplify your answer. But he can definitely, I'm sure he will specify what he wants. But the idea here is that at this juncture, I don't really care, or we don't really care about testing your ability to do algebra, right? This is not an algebra question. This is a do you know the quotient question? And I don't want to penalize you for not getting the algebra right. So that's usually the thought process there. Those kinds of questions. Let's do a couple more. So let's say I want to find the derivative of. Also, I should point out there's lots of notation for finding the derivative of, right? I am very much a fan of writing the derivative of like this because it's kind of the least amount of writing. So I'm saying find the derivative with respect to x of the function x cubed plus 5x minus 7 over cosine of x plus 8. But someone else might write this as something like for f of x equal to x cubed. Guy, it's terrible even just starting it this way. For f of x equal to that, find f prime of x. That is an equivalent statement. Both of them are asking us to find the derivative of this thing. All right, I want you all to do it. Find the derivative of this using the quotient rule. You guys at home too. Shouldn't be doing it on your own or wherever you are. I always assume people on Zoom are at home, but like you could be anywhere, right? So normally I wouldn't write this step, but it is a perfectly reasonable step to write. I'm just literally writing out the words in my head. It's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, all over the bottom function squared. If you prefer, it's totally fine to write the derivative of this times that. For like, you can change the order here. It doesn't matter which way you write it. This is just the way I do it, right? People have their own preferences. You can do it your way. I can do it my way. We're doing the same thing. But we can't just leave it like this, right? Because we actually haven't finished the problem. So we do actually have to find the derivative of this and the derivative of this to finish the problem. So let's write this as cosine of x plus 8 times 3x squared plus 5. Minus, actually before minus, do I need parentheses around the 3x squared plus 5? I really do. And here's why. It has to be all of this times all of that. If you just leave it like this, and someone's taking you at face value, what you have written 3x squared times cosine x plus 8. And then after you do the multiplication, then you add on 5. If you don't write parentheses there, the only multiplication applies to just the next term after it. So we really have to write parentheses here so that if you were to multiply this out, you'd have to FOIL it out and do this times this, this times this, this times this, this times this. So definitely, if your things have more than one term in them, in the product rule or in the quotient rule, you really need to slap on some parentheses around them so that you get the entire multiplication. Same deal over here. I'm going to get x cubed plus 5x minus 7. And what's the derivative of cosine x plus 8? Negative sine x. So what I would probably do here is I would probably say instead of times negative sine x, especially because I don't even want to write it down here. If I just wrote negative sine x here, someone might think I meant subtract sine of x. So if you really want to write times negative sine of x, you should write times parentheses negative sine of x so that you can see the multiplication and not the subtraction. And then bottom is still the same as it was. You almost never multiply out the bottom. And I'm definitely not going to multiply at the top here. One simplification I would have done here is I would have actually written this second part as plus x cubed plus 5x minus 7 times sine of x. I would have brought that minus sign to the front there to change it. That's totally valid. A minus times a minus is a plus.
Would they ever ask to do you think they would ever ask a question like simplify this and then?
So simplify is not a good word to use here because multiplying it out is really not making it simpler. No, this question I don't think is one someone would ask you to expand or simplify just because it doesn't make it any nicer. We'll get to those kinds of questions where you do want to simplify it because there are reasons to, but something like this is just, it's a derivative for the sake of doing a derivative. Let's do one more. Yeah, let's do one more like this. Well, kind of like this, and then we'll talk about the rest of the trig functions. Let's say I want to find the derivative of, what have we got here? Sure. X squared times sine of x over x to the 4th plus 1. I don't know why I put parentheses around that, but I did. No good reason there. I just happened to write one, so I had to finish it off. So I will point out, not only do we have a quotient rule, we also have a product rule within this quotient rule, because the numerator is the product of x squared times sine of x. So to find the derivative here, it's going to be, well, again, if you're James saying words in his head, you're going to say it's the bottom times the derivative of the top. And here I might just write x squared times sine of x prime, because I don't want to have to think about doing the product rule right this moment. Minus the top times the derivative of the bottom, which is 4x cubed. I don't need parentheses around that 4x cubed. It's one term. It's not negative. So you could write parentheses. It'd be totally fine to write parentheses, but you don't have to write them there if it's only one thing. And then on the bottom here, we're going to get x to the 4th plus 1 cubed. If it's cubed, what am I doing? What should the power really be? Squared. So I think I saw the cube there, and it just, sometimes your brain does weird things. All right, but then we still have to take the derivative of x squared times sine of x using the product rule. So we're going to have x to the 4th plus 1 times the derivative of this product, which is 2x times sine of x plus x squared times cosine of x. Derivative of x squared, leave sine alone, plus leave x squared alone, derivative of sine. Minus, if you really felt the need to simplify it, you could say 4x cubed times x squared is 4x to the 5th times sine of x. all divided by x to the fourth plus 1 squared. Okay, here's a question that I'm hesitant to ask, but I should ask it. Can I cancel an x to the fourth plus 1? I cannot. Definitely not. I could if I could factor 1 out from both this term and this term. But since there isn't an x to the fourth plus 1 there to factor out, I can't. Later on, we see some other quotient rule things after we've talked about the chain rule. We'll see some factoring that sometimes occurs for these kinds of problems. But let's go ahead and talk about the derivatives of the rest of the trig functions, because now we can find them. Oh, now that we have the quotient rule. And I feel like he did them slightly differently, which is totally fine. I think he did them as a product rule kind of deal. It's not my favorite, but it's totally fine. But let's talk about the derivatives of the trig functions. Because there are 4 functions we have not written yet. So I would encourage you to memorize these at some point, and I would definitely encourage you to write them in the following order. So we're going to make a little list here. We'll come back and fill it in. So yeah. So the derivative of sine is cosine. The derivative of cosine is negative sine of x. And we're going to fill in the derivative of tangent. And then over here to the right, we're going to write all the reciprocal functions. So the reciprocal sign is cosecant. So we're going to do the derivative of cosecant, derivative of secant, and the derivative of cotangent. Those are all on the agenda. And there's actually some really nice patterns to see when we find these. So let's talk about the derivative of tangent first. So to find the derivative of tangent, I want to write tangent as sine over cosine. Oh, look, a quotient. I know how to take the derivative of a quotient. I'm going to use the quotient rule. So that's going to be the bottom times the derivative of the top. And the derivative of sine is cosine. Minus the top times the derivative of the bottom. And the derivative of cosine is all divided by cosine squared of x. Okay. But now we have to know something. Well, actually, let's rewrite this before we have to know something. That's equal to cosine squared of x plus, because the minus times the minus is a plus, sine squared of x, all divided by cosine squared of x. And cosine squared x plus sine squared x is everyone's favorite trig identity, or at least it's the most famous one. And it's equal to 1. So the top here is just 1 over cosine squared x. And you could leave it like this, but no one ever does. Instead, we say, well, 1 over cosine is secant. So 1 over cosine squared x is really secant squared of x. So the derivative tangent of x is secant squared of x. Cool. Questions? How do I want to say that? Yeah, let's do the next one. So let's in a similar way, find the derivative of cotangent. Because there's a really nice thing I want you all to see. So same deal, derivative of cotangent. I'm going to write cotangent as, so you could do the thing where you write cotangent as 1 over tangent. This is not my favorite. I would rather write it as cosine over sine. It's not wrong to do it a different way. It's just not the way I think looks the nicest. Same deal. We have a quotient. We're going to use the quotient rule. So it's going to be the bottom times the derivative of the top. The derivative of cosine is negative sine minus the top times the derivative of the bottom, which is cosine, all divided by sine squared of x. So now on top, I have negative sine squared x minus cosine squared of x over sine squared of x. What's negative sine squared minus cosine squared equal to? Or maybe what could I factor out to make it easier to see? If I factor out a -1, I'm left with sine squared x plus cosine squared x all over sine squared x. And then we know that sine squared x plus cosine squared x is equal to 1. So I have a -1 on top over sine squared, or a -1 times cosecant squared x. So the derivative of cotangent of x is negative cosecant squared of x. Here's the pattern that I want you to see because it's nice. It kind of takes a little bit of just looking at the words for a second. So we have 6 trig functions. The co-functions, cosine, cotangent, and cosecant, and the regular not co-function. There's not a good name for the not co-functions, the other ones, sine, secant, and tangent. Listen to the words I'm about to say. The derivative of tangent is secant squared x. I'm going to put a co in front of each of those words. So tangent gives me, the derivative of tangent gives me secant squared. The derivative of cotangent gives me cosecant squared, but it's negative. We're going to see a similar thing being true for these derivatives here, but I want you to be ready for it. So let's look at the other two, and then we won't be done with these, but we'll have our full list. So let's find the derivative of secant. So I'm going to write the derivative of secant as the derivative of 1 over cosine. Oh, I knew there was something else I wanted to talk about. That's fine. Quotient rule again. This is all the quotient rule. So it's going to be the bottom times, what's the derivative of the top? What's the derivative of 1? It is 0, yeah. Derivative of constant is going to be 0. Minus the top times the derivative of the bottom. Derivative of cosine is negative sine, all divided by the bottom squared. Okay, let's simplify this a bit. That's just 0. -1 times minus sine is positive sine. So I have sine of x over cosine squared of x. And just like we don't leave the previous one as 1 over cosine squared, we don't leave this way. We typically rewrite this as 1 over cosine times sine of x over cosine of x. And 1 over cosine of x is of x, and sine of x over cosine of x is of x. So the derivative of secant of x is secant of x times tangent of x. And we're still going to do the last one, but we're going to guess what it's going to be first. So derivative of secant of x is secant of x times tangent of x. All right, so if the derivative of secant is secant times tangent, the derivative of cosecant should be, right, cosecant of x times cotangent of x, and it should be negative. So for any trig function and its derivative, you can take that one and just change all the things to the corresponding co-functions. So the tangent and the secant change to cotangent and cosecant. The secant and the tangent, sorry, the secant and the tangent change to cosecant and cotangent. It even works for sine and cosine. The sine and the cosine change to cosine, and the co-function of cosine is sine. This really does work for all of them. It's kind of neat. It's kind of like a light switch. You turn it on or turn it off. So if it already has a co, you go back to not having a co, and vice versa. Well, let's go ahead and show it just to make sure that we really are getting the right thing. So we take the derivative of cosecant of x. Well, the derivative of cosecant is the derivative of 1 over sine. That's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. It does end up being negative cosine x over sine squared x, which we're going to separate in the same sort of way. It's negative 1 over sine of x times cosine x over sine of x, which is equal to negative cosecant of x times cotangent of x, which is exactly what we said it was up there. So now we have all 6 trig derivatives, and you should memorize them. I have certainly recommended to students in the past, make it the lock screen on your phone. And just every time you look at your phone, you'll be like, oh, there's the trig derivatives. I should spend a minute making sure I memorize them. I did it when I had to memorize something else for a class I was teaching, and it really helped me actually, I was like, oh yeah, shoot, I should think about that for a second. And I memorized it. There were a lot of things to memorize. And I was like, okay, I can do this if I just do it this way. Oh yeah. So one other thing about this. So I have memorized these because I've seen them 1,000 times, probably at least. You have not seen them 1,000 times yet, so you might not have memorized them yet. I recommend writing them this way because sine divided by cosine is tangent, and then I can just have the reciprocals next to them like this. I will also tell you, one student I've seen told me that they found a way of doing it, which they did this. So when they're trying to specifically remember sine and cosine, you just have to memorize. Like they're going to be there all the time. For secant and cosecant and tangent and cotangent, they did this. They wrote, how did they do this? Yeah, they did this. So they wrote tangent and then an arrow to secant and then an arrow coming into secant from secant. So that the derivative of tangent is secant times secant, which is secant squared. And the derivative of secant is secant times tangent, secant times tangent. I thought it was kind of clever. And it also works for if you do cotangent going to negative cosecant and then cosecant. Derivative of cotangent is negative cosecant times cosecant. Derivative of cosecant is negative cosecant times cotangent. So if you like that, it's easy to write down if you remember what's going on. I thought it was clever. I certainly didn't come up with it. I wish I could claim credit for it. Questions about any of these trig derivatives before we do more things? There are other ways of getting them. These are the ways I think are the nicest. But it doesn't really matter which way you get them as long as you can remember what they are. All right. So now we can ask even more interesting product and quotient rule questions like, what's the derivative of x to the 9th power times secant of x? Okay, well, still the product rule as it ever was. It's going to be 9x to the 8th times secant of x plus x to the 9th times the derivative of secant is secant of x times tangent of x. And that's kind of it. Sure. There's something here I wanted to say. Oh, I know what it was. Let's look at these two specific questions. What if I want to find the derivative of 5 times cotangent of x? Can I use the product rule here? I mean, sure, I have a product. But here's what I want you to see. So if we use the product rule here, we're going to get the derivative of 5 times cotangent plus 5 times the derivative of cotangent. What's the derivative of 5? Right. And then 5 times the derivative of cotangent is negative cosecant squared of x. The point I want to make, because this comes up a lot, is that when you have the derivative of a constant times a function, that constant just hangs out and you end up multiplying it by the derivative of that function. So we really do just get negative 5 times cosecant squared of x, or 5 times the derivative of cotangent of x. It also works when you divide by a constant. So for example, excuse me here, if I was going to take the derivative of, say, sure, 3 sine of x plus x squared all over 7, there's no good reason to use the quotient rule here. Because really, we should think of this as the derivative of 1/7 times 3 times sine of x plus x squared. Or if you prefer, even distributing the 1/7 and writing it as the derivative of 3/7 times sine of x plus 1/7 times x squared. Dividing by a constant is the same as multiplying by a constant. It's just the reciprocal of that constant. So now I can just not use the quotient rule and say I get 3/7 times the derivative of sine, which is cosine, and I get 1/7 times the derivative of x squared, which is 2x. So when you're dividing something by just a constant, you really, really, really probably don't want to think about using the quotient rule. Oh yeah, we should do one of those. What time is it? Oh yeah, we got loads of time. find the equation. Can I write? Yes, I can. Of the line tangent to f of x equal to, let me make sure I'm not doing anything super dumb here. X squared plus 1 over x cubed plus 2 at x equal to, sure, that works just fine. Yeah. Equation of a tangent line. All my papers are super out of order. That's fine. I'll live. Okay. So whenever someone says find the equation of a tangent line, we always know there are two things we need to find. We need a point and a slope. Sometimes they just give you all the point. Here we did. I didn't give you all the point. I gave you half a point. I gave you x equal to 2. We also need the y coordinate. So the point, if x is equal to 2, y is going to be f of 2, which is 2 squared plus 1 over 2 cubed plus 2, which is 5 over 10, which is 1/2. Cool. All right. In a calculus class, someone says in a calculus class, they mean we should be talking about derivatives. That's like the big hint. Like in a calculus class, and we're trying to find the slope of the tangent line. How do we find the slope of the tangent line? By taking the derivative. So we find the slope by taking the derivative. Also, that's the only thing we can do, really. Like we don't have two different points to find the slope between. So here, my derivative is going to be, it's going to be kind of gross. It's going to be the bottom times the derivative of the top, which is just 2x, minus the top times the derivative of the bottom, which is 3x squared, all over the denominator squared. I don't think there's any good reason to simplify this, but I do need to plug in the x value to find the actual value of the slope. So there's my derivative in general. F prime of 2 is going to be 2 cubed plus 2 times 2 times 2 minus 2 squared plus 1 times 3 times 2 squared, all over 2 cubed plus 2 squared. I think you should do whatever level of mental math you are comfortable with and not write all this out. If I was doing this, I probably would have started by saying, oh, okay, 2 cubed plus 2 is 10. 2 times 2 is 4. 2 squared plus 1 is 5. And 3 times 4 is 12. All divided by 2 cubed plus 2 is 10 squared. So I've got 40 minus 60 over 100. That's negative 20 over 100. That reduces to negative 2/10 or negative 1/5. So then the equation of our tangent line is y minus the y coordinate, which was 1/2, equal to your slope times x minus the x coordinate, which was 2. And usually you're going to get asked to solve for y here. Like I would love to leave it like this, but most of the time people are going to be like isolate y. So I would write this as negative 1/2, y minus 1/2 equal to negative 1/5 x. Negative 1/5 times negative 2 is positive 2/5. I'm going to add 1/2 to both sides. So we get negative 1/5 x plus 2/5 plus 1/2. 2/5 is 4/10. 1/2 is 5/10. So I really have 9/10 altogether. So y equals negative 1/5 x plus 9/10. That's how I would end a problem like that if I had to solve for y and get the y-intercept. All right. Quotient rule, chain product rule, trig derivatives. Covering a lot today. We should probably also talk about the chain rule. Yeah, let's go here. Let's say I want to find the derivative of, how do you get an example? Yeah, x to the 5th plus 1 cubed. We could multiply this out. In fact, we're going to multiply this out. So sometimes, lots of times, when you're trying to take a derivative, just simplifying the thing first is a good idea. It makes it easier. Sometimes. Lots of times. And I'm going to multiply this out using, what's that thing called? Pascal's triangle. I was almost going to say the Pythagorean triangle. No, Pascal's triangle. So it's going to be, I'm still taking the derivative, right? I haven't taken the derivative yet. So I still need to write the symbol that's saying take the derivative. So I'm going to x to the 5th cubed, which is x to the 15th, plus 3 times x to the 5th squared times 1, plus 3 times x to the 5th times 1 squared, plus 1 cubed. All right, that's my 1, 3, 3, 1 pattern with, yeah, my 1, 3, 3, 1 pattern. All right, and now let's take the derivative. We're going to get 15x to the 4th plus 3 times 10 is 30x squared plus 3 times 5 is 15x to the 4th. Okay. But this is not the way you should really do this. Especially because what if it was the 30th power or the 300th power? You can't, I mean, technically it is possible to multiply that out. No one has the time or the brain capacity to actually multiply that. No one's doing that in their head, just on paper. So here is the thought. And here's how I really want you all to see this. If I'm taking the derivative of x to the 5th plus 1 cubed, I have the derivative of something cubed. Or as I will often say, some stuff cubed. I like the word stuff a lot. What's the derivative of x cubed? Everybody. How much x? 3x squared. All right. Derivative of x cubed is 3x squared. If the derivative of x cubed is 3x squared, what's the derivative of some stuff cubed? Same pattern. 3 times the stuff squared. There's a little bit more to it, but we're going to start there. So we're going to get 3 times the stuff squared. Let's look back at the previous one for a second. I should have done some factoring here. Wow. That should have been how did you guys let me get it? I said the right words, right? I feel like I said 14. I'm just losing am I losing my mind? I might be losing my mind. 3 times 10 is 30x to the 9th. Holy smokes, what happened there? I know it's on me to like teach this correctly, but also you all are responsible for making sure I don't do dumb shit. So if you see something that looks crazy, point it out, please. Clearly I don't know what's going on. All right, what can I factor out? Let's make sure it's all right. Okay, I think it all looks right. Okay, what can I factor out from all 3 of these terms? A 15 and an x to the how much? Well, I have an x to the 14th here, an x to the 9th here, an x to the 4th here. I can factor out an x to the 4th, right? I can't factor out any more x's than that because I won't have enough here if I do that. So if I do that, I'm left with a x to the 10th plus a 2x to the 5th plus 1. I'm going to rewrite this in a slightly more suggestive way. Instead of writing 15x to the 4th here, I'm going to write this as, I'm going to point out that 15x to the 4th is 3 times 5x to the 4th. So I'm going to put the 3 in front. My parentheses I'm actually going to change, so don't fill that in yet. And I'm going to have my 5x to the 4th out here. And I will tell you that x to the 10th plus 2x to the 5th plus 1 factors as x to the 5th plus 1 times x to the 5th plus 1. So notably, the difference between what I actually know the derivative is equal to and the thing I've written down here, I'm off by what? Right. I'm off by a 5x to the 4th. I'm off by a derivative of the inside stuff. And that is the chain rule in a nutshell. If you have some inner function and some outer function, we take the derivative of the outer function, leaving the inside stuff alone. And then after we have done that, we multiply by the derivative of the inside stuff. That is the gist in general. Let me show you another example. One that is hard, that we could not multiply out. So if I said I want to find like the derivative of x to the 4th plus sine of x to the 101st power. We're not multiplying that, but we don't need to, because we all know that the derivative of x to the 101st power is going to be 101 times x to the 100th power. And in a similar way, the derivative of some stuff to the 101st power is going to be 101 times our stuff to the 100th power. Then I have to multiply by the derivative of the stuff. So the stuff is x to the 4th plus sine of x. The derivative of the stuff is 4x cubed plus cosine of x. So we had some stuff to a power. The derivative was bring the power down, leave the stuff alone. Power is one less. And then after you have done the derivative of the outer function, then the derivative of the insides you multiply by. This is really an example of what's of the repeated product rule. Yeah, question.
So do you think since we're gonna all these rules, all the next term is gonna be like, oh, fine.
No, definitely not. We're done with limit definition. Over. Not really, but I mean, like, I can't imagine. Almost never do we have that kind of question on the second exam. We will still probably use the limit definition for a few things here and there, like the derivative of sine that he did in class. But in general, no, that's not going to show up on your next midterm, as far as I know.
Says that we wouldn't use it unless he's telling us the proof. So he'll give us, for example, like tangent is equal to its derivative, but prove that that's
Okay, but I would say usually the way we prove the derivative of tangent is secant squared is the way I did in class today.
Yeah,
By writing
that's the
tangent,
only
right? So that's not a limit definition question, right? That's a using the quotient rule to show the derivative. Yes, I would say he could definitely ask a question like that, but no, I don't imagine you would be asked a limit definition question. So let's continue talking about the chain rule because there's a lot more to say about it. Here's what I'll point out first of all. Yeah, so I know we haven't talked about it, but there is also something called a triple product rule and the quadruple product rule and the product rule of many things. It's really just the product rule. Let me show you. It's really fast. So we know that the derivative of a product is f prime times g plus f times g prime. If you took the derivative of a product of three things, well, the problem with the product, oh, I don't want to write that there, sorry. The problem with the product rule is it's literally defined to be the derivative of a product of two things. So here's what we're going to do. We're going to treat this like two things. There's one thing. There's the other thing. So for a product rule, it's the derivative of the first thing. Well, great. It's the derivative of the first thing, which we'll deal with in a minute, times the second thing, plus the first thing times the derivative of the second thing. But now, what's the derivative of the product f times g? Oh, it's right there. So we can re-expand this as, well, the derivative of f times g is f prime g plus f g prime, all times h, plus f times g times h prime. And then if we expand this out by multiplying the h through, we get f prime times g times h plus f times g prime times h plus f times g times h prime. The point of this is not that you really ever have to, like, someone could ask you a triple product question. For example, I could say, like, what's the derivative of x to the 7th times sine of 2x times tangent of x? And here I'd have to use a triple product. So it would be 7x to the 6th times leave the other two pieces alone. And then the derivative sine of 2x, I have to use the chain rule here. Derivative sine of x is cosine of x. Derivative sine of some stuff is cosine of the stuff times the derivative of the inside stuff. And then I leave the other two pieces alone. So I have an x to the 7th times the tangent of x. And then finally, the derivative tangent of x is secant squared of x and leave the other two pieces alone. And that's actually so the thing I was saying at the end there is actually the more broad idea of when you have a product rule of multiple things. For a product rule of any number of things multiplied together you want, It's the derivative of one piece times all the other stuff left alone, plus the derivative of the next piece times all the other pieces left alone. So for example, I'm not going to do it the long way. I'm just going to tell you if I was going to find the derivative of a quadruple product, f times g times h times j. Well, first of all, the derivative of product of two things, I got two pieces. The derivative of a product of three things, I got three pieces. The derivative of a product of four things, how many pieces am I going to get? Four. And each piece is going to have one derivative and the rest left alone. So the first piece is going to be f prime times g times h times j. The next piece, I'm not going to have f prime, I'm going to have g prime. So in each piece, you're getting one derivative, and each derivative has to show up at least once. So you get f times g prime times h times j, plus f times g times h prime times j, plus f times g times h times j prime. Why do we care? You guys, like, because you just like doing math. No, not because I just like doing math, although that's a good answer most of the time. Because this is where the chain rule is coming from. Well, a version of the chain rule. So let me just show you. What time is it? Okay, we got time. We got time. We got time. So let's say I want to find the derivative of f of x to the nth power. Well, when you multiply something to, when you have something to the nth power, like something to the fifth power, that means that something times itself 5 times. So when I have the derivative of f of x to the nth power, what it really means is the derivative of f of x times f of x times f of x. How many times? N times. Okay. But we know that if you have the product rule of n things multiplied together, well, just like when there were two things, we got two pieces, three things, we got three pieces, four things, we got, I'm gonna sneeze. We got 4 pieces. That's the worst. Excuse me. All right. When we have n things, we're going to get n pieces. And in each piece, we're going to get one derivative and the rest not derivatives. So when we take the derivative here, we're going to get f prime of x times a bunch of other f's. Plus f of x times f prime of x times a bunch of other f's. Each time the f prime is just moving one over. Sorry, it's a little bit messy, I know. All the way until the very last term is all these f's multiplied together. And the very last one is an f prime. All right, so 2 things. Thing 1, there are n of these. 1, right? So in the first one, the derivative is in the first spot. In the second one, the derivative is in the second spot. In the third one, the derivative is in the third spot. In the fourth one, the derivative would be in the fourth spot, and so on and so on and so on, until you get to the nth one, where the derivative is in the nth spot. Each of these things have n things multiplied together. One of them is f prime, and the other n minus 1 of them are all f. So here's what I really have. I have f prime of x times f of x to the n minus 1 power. But I have that here also. Right here, I also have f prime of x times f of x to the n minus 1 power. I have that here also. Every term has that same expression. F prime of x times f of x to the n minus 1 power. How many of these do I have? 1, 2, 3, 4. I have n of them. If I have n of the same thing added up, like if I had 5 plus 5 plus 5 plus 5, if I have 4 5s added together, it's just 4 times 5. If I have something plus something plus something plus something n times, I really have n times that something. I'm going to change the order so it looks nicer. Instead of writing this times this, I'm going to write this first. So I want to point out, and I'm going to say words that are slightly different here, the derivative of some stuff to the nth power is n times that stuff to the n minus 1 power, as we would expect, but then you have to multiply by the derivative of the inside stuff. And this is called the power rule version of the chain rule, because the chain rule is actually more broad than this. Your outer function doesn't have to be something raised to a power. It can be kind of anything. It's time. Okay. We got time. We got 12 minutes. So for example, I could ask the question, what's the derivative of x to the 5th plus sine of x minus tangent of x, all raised to the 80th power? And we could totally find the derivative of that. It's not terrible. It's going to be 80 times all of our stuff left alone to the 79th power. Now be careful here. It's really, really easy to want to write like 5x to the 4th plus cosine x minus secant squared x there. So when you're taking a derivative and you're using the chain rule, the stuff you started with has to show up again. The inside function can't completely disappear. It has to reappear. It's our guest star. It's going to stick around. So I'm going to get 80 times the same stuff raised to the 79th power. But then after that, we multiply by the derivative of the stuff. We're going to be saying that a lot. You do some stuff, that's terrible. You take the derivative, you leave the inside stuff alone, and then after you've done all that, at the very end, you multiply by what? The what of the inside stuff? The derivative of the inside stuff. Always multiply by the derivative of the inside stuff, which in this case is 5x to the 4th plus cosine of x minus secant squared of x. But your outer function doesn't have to be being raised to a power. For example, maybe our outer function is sine. Maybe I have sine of x to the 7th plus 9x squared plus 2. And I want to find the derivative of that. Let's just call this f of x though. So f of x is sine of some stuff. And my derivative is going to be. So it's really important to kind of get a good understanding of the inner versus the outer function here. The inner function is x to the 7th plus 9x squared plus 2. The outer function is sine of that. I always, if I'm using the chain rule, I'm differentiating the outer function first. So there's sine of some stuff, and usually, with some exception, but usually the language will help you see it. If you're saying sine of things, well, the of part, after you say the word of, that is usually your inner function. Sine is your outer function. There are a couple exceptions, but yeah.
So, like, if I saw this probably on the test screen, I would automatically think to do the power rule.
We are going to use the power rule, but before we use the power rule, we have to use the chain rule. So let me ask everybody, and you all should know the answer to this. What's the derivative of sine of x? Right. And I really encourage you to say the of x part. It is important to recognize that it's not the derivative of sine is cosine. I mean, it is, but really it's the derivative of sine of x is the derivative of cosine of x. So that then when your argument of your function changes, you are still saying the right thing. So the derivative of sine of x is cosine of x. The derivative of sine of some stuff is cosine of, and then we multiply by the stuff's derivative. Good. Yeah, I like that. And people always want to say we multiply by the stuff. And I'm like, no, it's the derivative of the stuff. Or the stuff's derivative is good. I like that. So here, the derivative sine of some stuff is going to be cosine of the same stuff. We leave it alone. But then we multiply by the stuff's derivative, where we're going to use the power rule, which is going to be 7x to the 6th plus 18x. And if you wrote it like that, I would at least knock off a point, because it's cosine of this stuff times all of this, which means you have to have, how much time? Okay, let's do a couple more of these because they are good to do. Let's say our function we want to take the derivative of was, so this next one I think is a little extra tricky just because of the nature of this specific type of function. What if I had secant of x to the 7th plus 9? Why am I doing the same functions? I don't know. 9x cubed minus 4. When I'm first encountering the chain rule, I'm always like, well, what's the derivative of my function of just x? What's the derivative secant of x? What is the derivative secant of x? So you definitely want to memorize these. Derivative secant of x is secant of x times tangent of x. Secant and cosecant are kind of unique in that, unlike most other functions where the stuff shows up only once in the derivative, for secant, the stuff shows up twice. Derivative secant of x is secant of x times tangent of x. Not secant tangent of x, by the way. I've seen so many people write secant tangent of x. Secant has to be of something. So the derivative secant of x is secant of x times tangent of x. The derivative secant of some stuff is going to be secant of the stuff times tangent of the stuff. Which seems weird that it shows up twice, but it definitely does. And then we have to multiply by. You guys are gonna get sick of it, but what is it anyway? The derivative of the stuff, which is 7x to the 6th plus 27x squared. And sorry, it's a little bit tiny in there. Yeah.
Why did you do secant times tangent and stuff?
Secant of what?
Secant of x, I mean, wait, but.
The point is you're answering your own question here with my question, right? The reason we don't write secant times tangent is because you have to take secant of something. Just like you can't take the square, we can't write the square root without there being something to take the square root of. Same is true for secant. There has to be an argument for any function. So it's really, really, I encourage you all to really train yourself to say secant of, tangent of, cosine of, square root of. The word of might be the most important word in all of math when you're dealing with functions. So when you're saying something and it's a function of something else, say the word of. It'll help you out immensely. So here, the derivative of secant of x to the 7th plus 9x cubed minus 4 is secant of that same stuff times tangent of that same stuff times the derivative of that stuff. And we don't get the derivative of that stuff coming up twice, even though the stuff shows up twice. Let's look at one more that's a little bit harder. Let's say I want to find the derivative of cosine to the 6th of x to the 4th plus sine of 3x. The reason this derivative is a little bit harder, in my opinion, is it's not immediately clear what the outermost function is. And I'll be perfectly frank, it is not cosine. So we read this as cosine to the 6th of x to the 4th plus sine of 3x, but I really, really, really can't recommend enough, when you have a power of a trig function that you have to differentiate, it is worth your ink to rewrite it as cosine of x to the 4th plus sine of 3x, all raised to the 6th power. We don't usually write this because it's annoying, right? We write this because it's just a nicer abbreviation here, but this really helps me see, oh, all this junk getting raised to the 6th power, the 6th power is the last function or the outermost function. So if I'm taking the derivative of something raised to the 6th power, it's going to be 6 times my something to the 5th times the derivative of that something. Now, here's where you might not be very happy with me. It's not my fault. The inside stuff is still complicated. The inside stuff is also going to require the chain rule to take its derivative. So at this point, especially since I haven't left myself very much room over here, I might just write literally cosine of x to the 4th plus sine of 3x. And then I'm going to take the derivative of that. So here's my 6 times my stuff to the 5th power. And then here's my derivative of my stuff. But now, if you've done a derivative and you still have a symbol that says you need to take a derivative in your answer, that means you're not done. We still have to keep doing it until we've actually finished taking all the derivatives. So now I've got some new stuff. I have to use the word junk if I've already used the word stuff. So I've got some junk here. What's the derivative of this junk? Well, I've got cosine of something else here. Actually, I meant to use junk for that part. Sorry. I've got cosine of some junk. What's the derivative of cosine of x? Positive or negative? Negative, right? All the co-functions have negative derivatives. Cosine, cotangent, cosecant. Derivative cosine of x is negative sine of x. Derivative cosine of this junk is going to be negative sine of that junk multiplied by the derivative of the junk. It's always, right, when I say multiply by, it's always the derivative of the whatever. So we have to write all this other stuff down first. So it's going to be 6 times cosine of x to the 4th plus sine of 3x to the 5th. I suppose I could have written that as cosine to the 5th, but I didn't. Times the derivative of cosine of some new stuff. So it's going to be negative sine of that same new stuff, x to the 4th plus sine of 3x. And then I have to multiply by the derivative of the new thing there. What's the derivative of the inside part? Well, it's going to be 4x cubed plus, oh, I've used the chain rule one more time here. The derivative sine of some stuff is going to be cosine of that stuff times the derivative of that stuff. Kind of gross. Really gross. I'm not gonna lie, it's pretty gross. But not atypical. This is I would say this is a not unreasonable question to put on an exam where you're being asked about differentiation. All right. 10-20, should stop talking. So that's pretty much the chain rule. I mean, certainly you can do a lot more with the chain rule and the quotient rule and the product rule, and you can kind of mix them all together. So you could certainly have a function where you had to use like the product and quotient and chain rule all in the same derivative. It's kind of annoying, but it's not that terrible. Something else I want to say. Oh, I know what it is. If I haven't already posted it, I will post a derivative worksheet, which I will not lie, some of them are pretty gnarly, but I will also post the solutions to that. I highly, highly recommend, if you're looking for more practice, to do those problems, to try doing them without looking at the answers, and then later after you've done them, look at the answers. Always good to practice more. But definitely, I will say you want to get these rules down. Product rule, or to say power rule, product rule, quotient rule, chain rule. You want to know those by heart. You want to feel them in your soul. And then also the trig derivative, so that when you're doing the product rule, you don't have to look up the derivative of tangent or the derivative of secant or the derivative of whatever. So practice, practice, practice so you know them well. There is no substitute for practice. You just have to do a lot of problems so that you know these derivatives well.